In previous lecture videos, we have investigated the sampling distributions of the sample mean and the sample variance. In particular, we determined the mean and the variance of the sampling distribution of the sample mean, and we also determined the mean of the sampling distribution of the sample variance. Now, in this lecture video, what we're going to do is utilize that information to come up with estimators for the population mean and the population variance. Now, for simple random sampling, we've shown in a previous lecture video that an unbiased estimator of the population mean is given by the sample mean, x bar. And we are denoting this estimator, this unbiased estimator of the population mean, by mu hat. Now, we also showed in a previous lecture video that the usual sample variance, the version with n-1 in the denominator, while it's an unbiased estimator under IID random sampling, under simple random sampling, the sample variance s squared is not an unbiased estimator of the population variance. So we need to adjust that sample variance in order to come up with an unbiased estimator of the population variance. And the way that we do that is shown here in the middle of this slide. We have to take s squared and multiply it by n-1 over n, where n is the population size. You'll recall that it was shown and also demonstrated in an example that as an estimator of sigma squared, the sample variance is biased, and in particular, it tends to be too large. And so what we need to do is reduce it or attenuate it just a little bit in order to make it unbiased. And the factor that we multiply against it to make it unbiased is this quantity, this fraction, n-1 over n. And you'll notice here that that multiplicative factor is less than 1, and so this is in fact attenuating that sample variance. And so when we do this, what we end up with is an estimator that is unbiased for sigma squared. Now, we will denote this unbiased estimator of sigma squared by sigma hat squared. Then once we have the estimator of sigma squared, then to come up with an estimator, the corresponding estimator of the population standard deviation, we just take the square root of our estimator of the population variance. So we would take the square root of sigma hat squared, and that gives us then the corresponding estimator of the population standard deviation, which we will denote by sigma hat. All right, and so that's equal to the square root of cap n-1 over cap n times the sample variance, or we could pull s squared out and we would have the square root of cap n-1 over cap n times the sample standard deviation. Now let's use this formula for our estimator, unbiased estimator of the population variance. Let's apply this then in the example that we've been looking at and see, let's check to make sure that the estimator that we have is actually unbiased. Okay, so here is a template that we can use for this purpose. And I've got the sample number, the sample values for x1 and x2, and then the sample variance entered for each of the 30 samples. And then what we need to do is take this sample variance and adjust it according to this formula, multiplying the sample variance by n-1 over n for each of the samples, and put those values in this last column. And so these will be the estimates for sigma squared. In other words, these will be the values for sigma hat squared for each of the 30 samples. Then, once you have that, calculate the column total, the sum, and then divide that total or that sum by 30 to get the mean of the sampling distribution for sigma hat squared. Now, let's adjust all of these sample variances by multiplying by n-1 over n, and when we do that, these are the values we get. And so you can look here and you can see that these values are a little bit less than the sample variances in the column over. And so these are the values for sigma hat squared for each of the 30 samples. And when we calculate the average of these values, we get 95.5833. And that is the mean of the sampling distribution for sigma hat squared for simple random samples of size 2 from this population of 6 values. Now, so what we've just shown then from our empirical calculations is that for this example, the mean of the sampling distribution of sigma hat squared is equal to 95.5833, repeating, and that is equal to 1147 over 12. Now, what does the theory tell us should be the mean of the sampling distribution of sigma hat squared? Well, the theory tells us that the mean of the sampling distribution of sigma hat squared, or in other words, the expected value of sigma hat squared, should be equal to sigma squared itself, right? Because that's the whole point. We constructed this to be an unbiased estimator for sigma squared. And what that means is that it ought to be the case that the mean of its sampling distribution should be equal to sigma squared. Now, earlier we calculated the variance of this population. We calculated sigma squared to be 95.583 repeating. And so we see that we have agreement here. Empirically, the mean of the sampling distribution of sigma hat squared for this example is exactly what the theory tells us it should be. So that shows that for this example, these values would be the appropriate estimators for sigma squared for each of the 30 samples. Now, a related question is sigma hat an unbiased estimator of sigma? Remember, sigma is the population standard deviation. Our estimate of sigma is sigma hat. So the question is sigma hat an unbiased estimator for the population standard deviation? And so I have another template. And by the way, these templates are available on Moodle. Please download those and fill them out as you work through this set of lecture videos. So I've added another column to our previous table. Here was the previous table. We had the last column was sigma hat squared, and now I'm appending a column to the right that is going to be used for sigma hat. And the way that we get that, obviously, is just to take the square root of the values in the adjacent column. And so when we do that, here are the values rounded to 3 decimal places. And so then to find the mean of the sampling distribution of sigma hat for this situation, all we have to do is to calculate the mean of this column of numbers. And that turns out to be 8.564. And so going back to our question, is sigma hat an unbiased estimator of sigma? Well, from our empirical calculations, the mean of the sampling distribution of sigma hat, in other words, the expected value of sigma hat, is 8.5636. Now, recall that the population variance was shown to be 95.583 repeating, and so it follows then that the standard deviation of the population is the square root of that, which is 9.7767. Okay, now, since the expected value of sigma hat, the mean of the sampling distribution of sigma hat, which is 8.5636, is not equal to 9.7767, which is the population standard deviation, because those two values are not equal, it follows that sigma hat is not an unbiased estimator of the population standard deviation sigma. Sigma hat is biased as an estimator of sigma, the population standard deviation, and on average it tends to be a little bit too low, as you can see here as an example. All right, so next we're going to investigate properties of these estimators, or additional properties. We've already shown that both mu hat and sigma hat squared are unbiased. Mu hat being an unbiased estimator of mu, and sigma hat squared being an unbiased estimator of sigma squared. But we're going to investigate additional properties of these estimators. All right, so first we'll look at the variance and the standard error of the estimator of the population mean. All right, so under simple random sampling, the variance of the sampling distribution of the estimator of the population mean is given by this expression. All right, so we have here the variance of the sampling distribution of mu hat being our unbiased estimator of the population mean. All right, so the variance of the sampling distribution of mu hat is given by cap n minus little n over cap n minus 1 times 1 over little n times sigma squared. Okay, so this is the variance of mu hat. It is a function of the population size, the sample size, and the population variance. Now, once we have this, we can obtain the standard error of mu hat, the estimator of the population mean, by taking the square root of this quantity. All right, and so notationally, we will represent the standard error of the estimator of the population mean, in other words, the standard error of mu hat, by sigma sub mu hat, and it is equal to the square root of this quantity. So the square root of cap n minus little n over cap n minus 1 times 1 over little n times sigma squared. And again, we could pull the sigma squared out after taking the square root, and so we would have this equivalent expression for this. Now, for the example that we've been looking at, recall that the population variance is 1147 over 12, or 95.583 repeating. Applying these formulas, we would find then that the variance of the sampling distribution of mu hat, which is given by this expression here, turns out to be 1147 over 30, or 38.23 repeating, which we could also represent as 38 and 7/30. Okay, so this is the true variance of the sampling distribution of mu hat. Okay, the standard error of mu hat, in other words, the standard deviation of the sampling distribution of mu hat, would be the square root of this value, and so to 4 decimal places that turns out to be 6.1833. Now the problem with all of this, let me go back to the previous slide. Again, this is the true variance of the sampling distribution of mu hat. This is the true standard error of mu hat. But the problem is that we can't compute that. We cannot compute the true value because we don't know sigma squared. We don't know, or in general, in a real problem, we won't know the population variance. So we will not be able to compute the variance of the sampling distribution of mu hat. And if we don't know the population variance, we won't know the population standard deviation. And so, again, we will not be able to compute the standard error of mu hat in a real-world problem. Okay, so while it's nice in an example to be able to compute these things in the real world, we wouldn't be able to calculate these. But there is value to knowing these expressions, because now that we know these expressions, for example, for the true variance of the sampling distribution of mu hat and the true standard error of mu hat, if we can obtain estimates of sigma squared, then we can estimate the variance of the distribution of mu hat, and we can estimate the standard error of the distribution of mu hat. And we've seen how to estimate sigma squared. And so that's what we look at next. So an unbiased estimator of the of the variance of the sampling distribution of the estimator of the population mean. Boy, that's a mouthful. Let's think about that. Let's try to wrap our heads around that. Let me say it again. An unbiased estimator of the variance of the sampling distribution of the estimator of the population mean is given by these expressions. So I've got two equivalent expressions here. One in terms of sigma hat squared, our unbiased estimator of sigma squared. I also have it expressed in terms of the sample variance. Okay, and because this is an estimate of the variance of the sampling distribution of mu hat, we're going to put a hat on it, right? That we always put a hat on our estimates. And so sigma hat squared sub mu hat is equal to capital N minus little n over cap n minus 1 times 1 over little n times sigma hat squared, which is our estimate, our estimator for sigma squared. Expressed in terms of the sample variance, it's equal to, it turns out to be cap n minus little n over cap n times 1 over little n times the sample variance. So either of these formulas can be used, and as long as we do the calculation correctly, then we'll get the same exact answer. All right? Now, once we have our unbiased estimator of the variance of the sampling distribution of mu hat, then we can take the square root of that value to get the corresponding estimator of the standard error of the estimator of the population mean. All right, and we'll denote that estimator by sigma hat sub mu hat. So this is the estimated standard error of mu hat, and that's equal to the square root of cap n minus little n over cap n minus 1 times 1 over little n times, and we have sigma hat outside of the square root sign. We could also have sigma hat squared inside the square root sign if we want to do that. Expressed in terms of the sample standard deviation, we have this formula here. So sigma hat squared sub mu hat, that is an unbiased estimator of the true variance of the sampling distribution of mu hat. And so what we want to do next is to demonstrate that fact for the example that we've been looking at. And so I have yet another template that you can download and utilize. And I've noticed that I have got a column here for sigma hat squared sub mu hat. So this is a column for the estimated variance of the sampling distribution of mu hat. And so what we would do is, and we can calculate this column using either the sample variance column or the column containing mu hat squared. All right, and so then we would use either of these two formulas, and you might try using both just to make sure you can, you get the same answer. Okay, so when we apply the formula, these are the values that we get. Okay. And so these are again, let's think about what these values represent. Each of these values is the estimator for the variance of the sampling distribution of mu hat for the corresponding sample. Now, what we want to do is to calculate the mean of these values, and that will give us the mean of the sampling distribution for sigma hat squared sub mu hat. And it turns out to be 38.233. Now, let's go back to the example that we just looked at, and we can see here that that is equal to the true variance of the sampling distribution of mu hat, 38.23 repeating. Okay, and so we have demonstrated, again, from our empirical calculations, okay, we have just shown that the expected value of sigma hat squared sub mu hat, in other words, the mean of the sampling distribution of sigma hat squared sub mu hat, is equal to 38.23. Now, from the theory, we know that the true variance of the sampling distribution of mu hat ought to be, according to this formula, 38.23. And so we've seen those match, don't they? And so we've seen for this example, this demonstrates that the expected value, the mean of the sampling distribution of sigma hat squared sub mu hat, is in fact equal to the true variance of the sampling distribution of mu hat. And so this implies then, at least for this example, that sigma hat squared sub mu hat is an unbiased estimator of sigma squared sub mu hat. Okay? This is not a proof of the general result, it's a demonstration of this particular example, but the result does hold in general. All right, next what we're going to do is to calculate the margin of error associated with the estimator of the population mean. And we're going to use this approximation where instead of using, say, a z-value of 1.96 for a 95% margin of error, we're going to just round that to 2, right? So we talked about that in a previous lecture video, and this is where we're going to start utilizing this approximation. So the margin of error for an approximate 95% confidence interval estimate of the population mean mu is given by twice the estimated standard error of mu hat. In other words, 2 times the square root of cap n minus little n over cap n times 1 over little n times, and then we have outside of the square root sign, we have the sample standard deviation. Now, again, we could use either of these two formulas to get the estimated standard error of mu hat. So just pick whichever one you want to use. I've expressed it on this slide in terms of that particular formula. All right. Now, once we have the approximate, the margin of error for an approximate 95% confidence interval for mu, then we can very easily construct the confidence interval by subtracting this quantity from mu hat to get the lower endpoint and adding that quantity to mu hat to get the upper endpoint. Okay, and so this is the form for that confidence interval. We see we have here mu hat minus the margin of error to get the lower endpoint, and to get the upper endpoint we have mu hat plus the margin of error. So let's look at an example. This is example 5. An audit of a hospital's outstanding receivable accounts is to be conducted, one goal of which is to estimate the average amount due among all open accounts. So perhaps this is an old system where the accounts are kept in paper files, and they don't have time or the manpower to go and pull all of the files and enter that, or use that data to calculate the average amount due. And so what they want to do is they want to select a simple random sample of these accounts and then use the data that they obtain to estimate the average amount due among all open accounts. So suppose that there are 1,000 open accounts and that a simple random sample of 200 accounts is selected. So in this case, the population, it's a finite population containing 1,000 members or observations, and we have selected a sample size of little n equal to 200. Now, the average amount due in the sample was found to be $94.22 with a sample variance of 445.21. Okay, so use this sample information to estimate the average amount due among all 1,000 open accounts. Calculate the approximate margin of error associated with this estimate, and then construct an approximate 95% confidence interval estimate of the average amount due. Okay, so we have here a population size of 1,000, a sample size of 200. The sample mean was $94.22. The sample variance was $445.21 squared. Remember that the units on the variance is the square of the units of the original data. So the variance here is $445.21 squared. We then take the square root of that to get the sample standard deviation, which rounded to 1 decimal place is $21.1. All right, so those are the basic summary statistics for the sample, and then what we're going to do is use those values to come up with a point estimate and a confidence interval estimate for the average amount due among open accounts. Okay, so we know that the unbiased estimator of the population mean is equal to x bar, the sample mean, and so mu hat is equal to $94.22, so $94.22. Okay, and then next we calculate the estimated margin of error. All right, notice that I've got a hat on this margin of error, and it's going to be an approximate 95% margin of error. And so that estimated margin of error is 2 times the estimated standard error of mu hat. That is equal to 2 times the square root of cap n minus little n over cap n times 1 over little n, and then outside of the square root sign is the sample standard deviation, S. Okay, so the sample size is 1,000. I'm sorry, the population size is 1,000. The sample size is 200. Right, performing this calculation, we get $2.669 rounded to 3 decimal places. And so now that we have the point estimate for the population mean, $94.22, and the estimated approximate 95% margin of error associated with mu hat, we can then construct the approximate 95% confidence interval estimate for the population mean amount due among all open accounts to be ranging from $91.55 up to $96.89. And so the way we would interpret this is we would say that we are approximately 95% confident that the true average amount due on all open accounts is somewhere between $91.55 and $96.89. Okay, let's look at another example. In this example, we have a simple random sample of 9 hospital records that was drawn for the purpose of estimating the average amount due on cap n equal to 484 open accounts. So again, the population size for this situation is 484. The sample values are given below. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9 sample values. So little n, the sample size is 9. All right, and so what we want to do is use this data to estimate the average amount due among all 484 accounts, calculate the approximate margin of error associated with this estimate, and construct an approximate 95% confidence interval estimate for the average amount due. All right, and so here is the basic information for this situation. Again, the population size is 484. The sample size is 9. We have a sample mean. When you calculate the summary statistics for that sample, the sample mean is found to be $40.89. And then let's see, here we have the total value of the sample total is $368. The sample standard deviation is $5.9727, rounded to 4 decimal places. The sample variance would be 31.7099, again, dollars squared. Remember that the units on the variance are the square of the units of the original data. All right, and once we have the summary statistics, the sample mean, the sample variance, the sample standard deviation, and so forth, then we can go about estimating the population mean and also constructing a 95% confidence interval estimate for the population mean. And so the point estimate for the population mean, mu hat, is equal to x bar, so $40.89. The margin of error associated with that estimate is 2 times the estimated standard error of mu hat. Okay, and so that is given by this expression here. And I'm using the version that is expressed in terms of the sample standard deviation. All right, and so the population size is 484. The sample size is 9. The sample standard deviation to 4 decimal places is 5.9727. And so when we carry out that calculation, we get an estimated margin of error of $3.945. And so now that we have the estimated or the point estimate of the population mean and the approximate 95% margin of error associated with that point estimate, we can construct the approximate 95% confidence interval estimate for mu. All right, so $40.89 minus plus $3.945. And so we get a 95% confidence interval estimate that ranges from $36.94 up to $44.83. And so again, we can say that we are 95% confident that the average amount due is between $36.94 and $44.83. Alright, so that wraps up this lecture video. We'll continue on with the next material in the next lecture video.